two routes for the preparation, and each one has different methods of preparation. Of course, the chemistry of nanoparticles mainly depend on two factors. The first one is synthesis of nanoparticles, well controlled, and the molecular approach of more selective applications. Of course, I'd like to remind myself and you that the main advantage of using surface of getting or the main method which which we can get high surface area is to divide large particles to very small particles. This means we make division. This is the same way we prepare nanomaterials, and these are what can I say? The surface area has a great effect in all aspects or in all the purpose we use nanomaterials. Surface area. We will check this and we will look at this just now. There are some differences between bulky materials and nanomaterials. What are the differences between bulky materials and the nanomaterials? Actually, there are two properties or two types of properties. The first type of property is the physical properties. The second type of properties is the chemical properties. Chemical properties, of course, like reactivity and catalytic activity, both of them has a great difference between the use of bulky materials and the use of nanomaterials. For bulky materials, some materials like gold, for example, doesn't work at all. It is inert. That's why we or women wear gold as like a ring or a bracelet or something like this, because it doesn't react with anything. But you can't make the same thing with iron, for example, or steel, because it will react sometime with some things. So gold is inert, but when it goes to nanoscale, it changes its activity changes completely. It becomes very active material, and we will see in next slides. For reactivity, for example, some materials has low activity in some reactions, but whenever it goes to nanoscale, its activity changed completely as well. So both in chemical properties it change, and also in physical properties. The physical properties it changes from nanoscale or from bulk scale to nanoscale. How comes? The optical. Like, do you remember this glass or cup, the couple of cups we just saw? The optical properties it changed from the angle we look at it, or from where do you put the light. Its color changes because of nano materials properties, optical properties. So and also melting point greatly change. In nanomaterials, the melting point greatly reduced. The vapor pressure, of course, changed from from nano scale to bulk scale, and also the optical material, the optical properties is changed because of the energy level spacing or quantum effect, which is plasmon resonance. I will show you what does this means. No, here, what is the effect here? I'll just mention about it. The optical properties changed. Why? Because there is an effect. If the particles, if the particles is little bit smaller and smaller and smaller, less than the wavelength of the light, this means when it goes to another level of optical properties. This is called energy level spacing. Now, this is the main effect of changing the main effect which causes all changes made by reducing the particle size from bulk scale to nanoscale, which is the surface area volume ratio. surface area volume ratio is very important. Where did it come from? It comes from, this is the particle size. Of course, the increase of particle size leads to decreasing the increase of particle size leads to increasing the bulk atoms and decrease of surface atoms. So surface atoms increases by decreasing the bulk the particle size. Surface atoms increases, surface atoms increases by decreasing the surface the particle size, and vice versa in case of bulk atoms. This is very important chart, very important relation, because it has a lot of changes in the material after after preparation. Because increasing the surface area, for example, increasing the particle size, decrease surface area, and of course decrease catalytic activity, because active sites are little bit smaller than the little bit smaller than the nanoscale. Surface area and volume are both important in studying the exchange of materials in chemistry. Volume, this is, please take attention. Volume refers to the amount of space inside of the object, whereas the volume tells us how much substance needs exchanging. In the surface area refers to the area exposed to the external environment, and surface area tells us how much of this substance can be exchanged. So the surface area tells us how much of the substance can be exchanged because these are exposed to the external environment. Generally, surface area is a unique character. Surface area leads to increased active sites and consequently increases the catalytic activity. What about the selectivity in nanoparticles? Selectivity in nanoparticles, or the what happens in selectivity if we use the nanoparticles? The nanoparticles has different changes, like exchange in surface area, like control of crystal structure and morphology, control of surface composition, and also exposure to crystallographic facets and increased number of edges, corners, and the faces. All of these factors changes the catalytic activity, and consequently the selectivity will change or will be better. The activity of nanoparticles, as I just mentioned, related to large surface area and structure and the shape of the prepared materials. Let's go to a very important topic, which is the types of catalysis. We just mentioned in previous discussions the types of catalysis are two types: homogeneous catalysis and heterogeneous catalysis. We mentioned about it. Homogeneous catalysis means all the components, like in the reactor, like reactants and catalyst and products, are the same phase. Whereas heterogeneous catalysis, the components in the reactor, like catalyst and reactants, have different phases. These are different stories in both of them. In homogeneous, please try to concentrate a little. Inhomogeneous means like you add a piece of sugar in a cup of water. What will happen? All sugar molecules may have the ability to contact water molecules. It's very easy to contact water molecules. At this stage, so the probability of making reaction is high. At this stage, selectivity will be high. At this stage, the conversion will be high. Okay? And the probability of making reaction is very high. Okay, this is a story. The opposite story in heterogeneous catalysis. If we add just some liquid or gas and with solid catalyst, what will happen? only the surface of the catalyst will work. Only the surface of the catalyst will work. The bulk of the catalyst is out of scene. The molecules of the reactants can't see the bulk, so no reaction will be with the bulk. This will affect in the catalytic activity, the rate of reaction, and conversion, and selectivity, and everything. The only advantage, or the main big advantage of heterogeneous catalysis is that you can separate the reactants or products from the catalyst, or you can separate the catalyst from the medium of the reaction. This is the main advantage of heterogeneous catalysis. But on the other side, this is the biggest disadvantage in homogeneous catalysis, because you can't separate molecules of sugar out of water or something like this. This is the main disadvantage. Also, there is another disadvantage in the same disadvantage is also there in heterogeneous catalysis, but it is with little amount. Only leaching of some of this catalyst will occur in the solution, and may cause some traces of the catalyst in solution. Traces, only few. And also in homogeneous, you can't separate all. Even if you use many techniques like chromatography or so, you can't separate all. Also, if you can separate all, it will cost you very much. Now, let's go to this story and see how can we treat in these problems and do it as follows. In homogeneous catalysis involves catalysis and reactants in the same phase. Okay, just homogeneous catalyst may be soluble molecules or ionic compounds, or ionic compounds or something, which are completely accessible by the reactants, and also soluble in the with the reactants. Of course, their structure and functional groups can easily be changed to result in chemo ratio and enantiomer selectivity, as we mentioned in previous discussion. The main disadvantage is difficult to separate from the final product or reaction mixtures, that we already mentioned all about this just now. So to make separation, you can use chromatography, distillation, extraction, and all of these will not do the job 100%, and also will cost you much. Okay. So the solution, they believed that the solution is to support these materials or homogeneous catalysis on a support, to immobilize these materials on a fixed support. Okay, and then we will work with these materials as heterogeneous catalysis. At this time, they found that they made a very big revolution. They made a very big achievement, that they could support these materials on a support, and then you can easily separate it. But the problem is still we have a problem of heterogeneous catalysis, which not all the catalyst will work, and also some leachings will happen and leave some traces of the catalyst in the solution. This is the solutions that they made, I just mentioned. It was entrapping immobilization of the catalyst on a support, or make attachment or reaction of this homogeneous catalyst with a support. Make a reaction to bind it together. Now, for heterogeneous catalysis, they found it has the same, it has many disadvantages as well, and the catalytic activity is low, and the catalytic activity is low, selectivity is low, and the conversion is low, and needs high temperature to occur, and it has many other problems. So also it has possible leaching of active catalytic sites from the solid support materials can also occur. So now we go to the solution. The solution is they found that the solution may be in the formation of nanocatalysis. Why do or why does the formation of nanocatalysis is the solution? Because in nanocatalysis, they could achieve the advantages of homogeneous catalysis and also the advantage of heterogeneous catalysis and avoid the disadvantage of heterogeneous catalysis and avoid the disadvantage of homogeneous catalysis. Because when you decrease your material from very big scale to very low or in nanoscale, this means you go towards homogeneous catalysis. If you decrease, because uh, please try to imagine, in bulky materials it's very big, and in homogeneous materials, which are ions and molecules, is very small. If you take this material, which are very big, to divide, and to go to this material which are very small, this means you are going to homogeneous catalysis. You are getting the advantages of homogeneous catalysis. You didn't go to homogeneous catalysis. You just try to achieve homogeneous catalysis advantages. And on the other hand, if you are here in homogeneous catalysis and you have some disadvantages like separation of the catalyst from the solution, and you try to take these materials to bigger scale, to nanoscale, and at the scale you can separate these materials from solution. This means you are trying to achieve the advantages from each other, from both sides, and discard or try to avoid the disadvantage of each one. Let's see here that, of course, this is the story that I just mentioned, and it is here the nanocatalysis. Nanocatalysis is a very important bridge between homogeneous catalysis and heterogeneous catalysis. How comes? In the advantage of homogeneous catalysis was where high activity, high chemo and radio selectivity, means high selectivity, and less reaction time. Reaction time is quite fast, means high rate. In the same time, in nanocatalysis, we can get the same advantages, which are high activity, high selectivity, and less reaction time. Because just I mentioned that you are trying to take the material from nanoscale, from homogeneous, from ionic scale, just a little to nanoscale. Just a little. You move the size little to nanoscale. You still can have the same advantages of homogeneous catalysis. In heterogeneous catalysis, it has some advantages, which are excellent stability, easy accessibility, and easy separable. This means in nanocatalysis, it has the same advantages, which are stable and easy separable. Because they are solids. You divide big solid to small solid. Still, it is a solid, but small solid. And its decrease, the decrease in its size makes it very close to the properties of the homogeneous catalysis. This is an intermediate state between homogeneous and heterogeneous catalysis. However, what are the disadvantages of homogeneous catalysis? Where the difficulty in recovery and recycling of the expensive catalyst, and this is stable. And it is not there in nanocatalysis because we can recover the catalyst because it is heterogeneous, and it's an advantage in heterogeneous catalysis. And the heterogeneous catalysis has this advantage, which is less catalytic activity and long reaction time, but it is not there in nanocatalysis. In nanocatalysis, reaction time is like advantages, like homogeneous catalysis. I have just remembered something I want to tell you in to let you imagine the case we are talking about, which is nanocatalysis and homogeneous, and it's between homogeneous and heterogeneous catalysis. If you compare, for example, there are three states of matter we know, and of course, besides plasma, if we compare the properties of gas, liquid, and solid, you will find that liquid is an intermediate case or intermediate state between liquid and the solid. Okay, liquid assembles or is similar to gas in some properties, and it's similar to solid in other properties. So it acts as a gas, as a fluid in some properties, like fluidity, like it takes the shape of the of the vessel and other things, and it resembles or similar to the solid in other properties like compressibility. It doesn't you can't compress the liquid, but you can compress the gas, and the other in other things. Uh, 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 Different properties. It is similar to solid, and the other properties it's similar to the liquid to the gas. Here in nanocatalysis, it had the advantages of homogeneous and had the advantages of heterogeneous and avoided the disadvantages here and disadvantages here. Besides, it has new advantage for nanocatalysis. What is it? It is like this. It is energy efficient, decrease the energy used. Also, it is atom economy. We just mentioned yesterday about atom economy, and atom economy is achieved in the using of nanocatalysis. Eco-friendly, efficient. Of course, people of green chemistry will like it very much. And I think this slide shows very carefully or very well how the difference between these three stages and the nanocatalysis. Now we are, I think, this is a complementary statement that it says that we can control the reaction by controlling the material we are trying to prepare. Like if we prepare nanocatalysis, you can control the size, you can control the structure, you can control the shape, you can control everything during preparation. And I think, or I am sure you know that preparation of nanocatalysis is much easier than preparation of any other materials. It is very easy. So people who are working in nanocatalysis, the field of nanocatalysis doesn't need anything except some tools to make characterization. But the preparation itself, anybody can do it just with very very simple equipments. You can prepare nanomaterials, but only you will need some tools to characterize, which you will need the same tools to characterize other properties. So characterization is a main problem in either ways. But if you go to prepare organic materials, for example, you will suffer a lot. But if you go to prepare nanomaterials, it's very simple. So, and also you can control the shape and the structure and the size. You can control. You can control everything. Everything under control. Now, there is a big question, which is nanocatalysis. Is it truth or hype? Is it truth? Yeah, it means is it a fact or just fantasy or imagination for those people who are working in catalysis that they are proud of themselves? We are working in nanocatalysis. Our science is nano science or nanocatalysis. What do you think? Is it a truth or not? Of course, they may be right, but they may be wrong. How comes? They may be right because we explained yesterday that the reaction occurs on very tiny, very small parts of the catalyst, which is the reaction occurs in on the nanoscale. But can I see it or not? Did I intend to do it or not? Did I prepare the site for this reaction or not? This means I didn't do anything of these. So I didn't intend to do it. So it is not belonging to nanoscience. Okay? But in the same time, it's actually occurring on nanoscience. Actually, it occurs on nanoscale. So they said, okay, let's make everybody satisfied. Everybody will be happy. Okay? We didn't prepare, but it occurs on nanoscale. Yes, they just said several researchers have catalysis is always nano, but of course, if we believe them, so we will ask them about a very big question: why does gold doesn't have, if it is in any way will happen, so why does gold doesn't have activity in bulk scale, but it has activity in nanoscale? This means it is always nano. This means it is not the same case. There is no reaction at some time. There is no reaction at some times. Then it is not working in nanoscale. But in the same time, they answer this question. Yes, it is not working in bulk. But when it goes to the nanoscale, several structure, several things, or several edges, or several high energy spots or high energy sites on the surface may be acceptable or may be accessible to make the reaction. Why is gold not active in its bulk state when it exhibits extraordinary catalytic activity? It is very active. Catalytic activity when reduced to nanoscale. It is very simple. And also there is another example, which is copper oxide or cobalt oxide, which is very active in nanoscale and less active in bulk scale. Of course, we can, it's a kind of debate. Catalytic interactions are always in the nanoscale. But of course, it is catalytically using something. It's okay. Now we will go to we will go to another slide, which is the effect of nanocatalysis in green science. It has many effects, and because it has many, as you can see, it makes many factors or many effects on the on catalytic activity. Number one, it's adapting magnetic nanocatalyst recovery. Number one, because adapting magnetic nanocatalyst recovery. Actually, this item is very important because people who are working in nanocatalysis invented, this is invention, or try to make new shape of catalyst, which is the core shell. Core shell. Especially core shell, because they use the unique property of magnetite, for example, with the properties of other materials which will be the shell later on. Okay, and we will explain it later in this lecture, inshallah. And this is number one, which is use the magnetic properties of the nanocatalysis to enhance the recovery of the catalyst. Means if you have some magnet and you have magnetite in the solution, you simply put the magnet on the wall of the glass and it will attract to all the material which has magnetite to the magnet. This means easily separation. And mixing ionic liquids with metal nanoparticles, this is the second. And then creating electrodes with nanocatalysts with improved redox properties. Of course, the electrodes are very important. And in the same way, the nanocatalysis is used in this way in fuel cell. We just mentioned about fuel cells yesterday. It is being there on the membrane to make the reaction of fuel and to burn hydrogen and release energy. But of course, it's very sensitive to carbon monoxide, as we mentioned as well. Encapsulating nanoparticles in nanoporous cavities like zeolites. We will discuss about zeolites today, inshallah. It has many cavities, many pores, which you can easily push and add or enter these nanomaterials inside these cavities. Of course, if you get a rod of metal, rod of iron, rod of steel, you can't put it inside the cavity of the zeolite, but you can do with the magnetic or the nanoparticles. Controlling the shape of metal and metal oxide. This is another advantage of these nanoparticles, which are you can control everything, the shape and also the size and everything. And then by controlling these factors, you can control the catalytic activity and selectivity, because selectivity and the catalytic activity are also related to the shape and also related to the size of the nanoparticles. Here we can see that the catalytic activity or the catalytic properties of nanoparticles depend on several factors, which are the size of nanoparticles, the shape of nanoparticles, composition, interparticle spacing. What does it mean? The interparticle between the materials on the surface. If the space of the between this material, the nanoparticles on the surface is large, it will give activity different from that when these materials have less interparticle spacing. The oxidation state and the support of nanoparticles. All of these materials, all of these factors affect the activity of nanoparticles for any reaction. Let's take one by one. The size of nanoparticles. Of course, there are several experiments or several articles have been published in this topic, which is the activity is it changes by decreasing or increasing the size of the catalyst. Like this, in this case, the relation is inverse. The smaller nanoparticles, the more catalytically active, because the smaller nanoparticles, of course, means increase of surface area, means increase of accessible active sites, and increase the catalytic activity. And there is something quantum size effect. This is also, I have it just mentioned now. Other researchers, sorry. Research speculating originally that this behavior could be, which is this reaction due to the quantum size effect. What is the quantum size effect? It describes the phenomenon where material properties change drastically when the size of material becomes comparable to the wavelengths of the electrons or other particles within it. Other particles within it, of course, this material has different particles. The size of reduction alters the electronic, optical, and other physical properties of the material. For example, this example is already mentioned there. This is the first factor, which is the size. What about the shape of the nanoparticle? The shape of nanoparticles, there are different shapes of nanoparticles, as we mentioned in previous slides, that there is spherical or hemispherical or rods or maybe cubic, different shapes, or core shell or star, or ring, different shapes. The shape is different. When the shape is different, of course, the catalytic activity is different. Like the case of the oxidation of CO by gold, nanoparticles in hemispherical nanoparticles were found to be more active than spherical ones. The hemispherical is more active than the hemispherical one. For other example, the silver nanoparticles, nanocubes, were found to be more active than nano spherical and triangular nanoparticles, as we can see in this figure in styrene oxidation. The reason for these dramatically changes are attributed to, of course, the increase or decrease in the relative area of catalytically active surface facets, or the differences in stability for different nanoparticles. This means that in the other slide, the size change makes different catalytic activity, and in here the shape change makes different catalytic activity. What about the composition of the active sites? The composition of the catalyst. If the composition changes, of course the catalytic activity changes. Like alloying of platinum with other materials, it will cause different catalytic activity. It will cause changes in the electronic properties, of course, and will change the catalytic activity. For example, alloying of platinum with rhodium or nickel or cobalt will change the catalytic activity of CO oxidation because of the poisoning of CO on these catalysts. What about the force factor, which, and this is an example data, which, however, the alloying of platinum with iron, rhodium, palladium, here the there is these are two, platinum and platinum oxide. In case of platinum, in case of platinum oxide, the activity of platinum itself is higher than the alloying, and in case of platinum oxide, it is different attitude, different behavior. In general, the change in the composition of nanoparticles, it changes the electronic structure of metal surface by the formation of bimetallic bonds, as well as the modification of metal bond lengths. The fourth effect is the interparticle spacing between nanoparticles. We just mentioned that the change in interparticle spaces will change the catalytic activity of the particles, like the catalytic activity of and stability of nanometer, 2 nanometer gold dispersed on the polycrystalline titanium carbide films displayed a strong dependence on the interparticle spacing. Because when it was 30 nanometer, the difference was 30 nanometer and 80 nanometer, it gave different catalytic activity. Like in this, of course, it is, I think, this data I have also just mentioned about it. Now we will go to the other factor, which is the I think it is the same idea. The oxidation state. Changing the oxidation state leads to increase or decrease the catalytic activity. It is not always the same behavior. Sometimes decreasing the catalytic activity, decreasing the oxidation state may increase the catalytic activity, and increasing the oxidation state may decrease the catalytic activity, case by case. I think these are changing the effect of platinum metal and the platinum oxide, and these are different cases about this. Now we will go to the support change. If the support change, it will also change the catalytic activity. Whereas if we use magnesium oxide as a support for gold, it will give different catalytic activity than other supports. And I think this idea has been already declared. Now we will go to other part, which is the core shell. Can we take a break for 2 minutes? Because you can use the same material as a core or as a shell in different cases or in different reactions. The inorganic core with organic shell, maybe magnetite with polymer, for example. Polymer, and the polymer may be prepared as a normal polymer or porous polymer. You can prepare it as well. Organic core with inorganic shell. Organic core, the same polymer we were using now, and inorganic shell like silica. Organic core with organic shell. Organic core and organic shell, both are organic. Shell, additionally, they exist various shapes like spheres, cubes, and prisms, something like that. This is a case of, again, these are not the only shapes of core shell. The left one is a core, or is a shell without a core. And of course, the left one is a core with a shell. The second one is a core, is a shell without a core. And the third one is a core but small. And number D is different cores with one shell. And number E, different shells with one core. And in this case, of course, each core will, each shell, if it is not the final one, will be a core for the next one. And these are different other different shapes. And of course, in this case, it is very nice to do it. This decoration. Of course, there is it is here. It is like this, or like this, or like this. But we added metal over this core shell to make a change in the catalytic activity and to attain different catalytic activity with different reactions. Let me show you something. And this is the core, and it is the same story that we mentioned. This is an example. We already prepared something like this. This is magnetite, and then we add titanium as a first shell, and this is magnetite with titanium, and this is the TEM of these materials. It is very clear and very beautiful, because you can see here that this is the core, very, very clear, and this is the shell. It is the same material, but this is using TEM, but this uses HR TEM. That's why I told you before that HR, which is a high resolution TEM, is used to closely show the shape and also the arrangement of the particles and atoms. It is very clear that this is the shell and the core, and also if the shell has well arranged or disarranged or not arranged. Of course, we can see that this is magnetite, and we prepare silica over magnetite, and again add titanium over the silica. And of course, it can be used in conventional method, like I'll show you how conventional method, and also it can be used in plasma-induced method. What's plasma-induced method? We use plasma to prepare these materials. And make decoration with metal like silver or like gold or palladium, according to what you are doing to do with this material. If you are doing to do this reaction, if silver is going to be good with this reaction, you add silver. And it's a kind of promotion of these materials with these metals. Let me show you. This is how we prepared it. We added magnetite. We prepared magnetite by mixing both ferrous and ferric for some time, make co-precipitation, and we obtained magnetite as nanoparticles like this. And we added TUS as a source for silica to make a shell of silica. Then again, we added titanium source to give a titanium shell. This means we have, how many shells we have? We have 2 shells, okay? And we make decoration with silver. we can make decoration with silver for this material by plasma or by conventionally by adding silver and reduce it over these materials. For the word reduced, I mentioned several times that reduction, sorry, the preparation of nanomaterials is much easier than preparation of any other thing. It's my opinion, okay? Because I will tell you a very simple experiment that if you bring silver nitrate solution, dilute silver nitrate solution in your laboratory and add a little bit, few milligrams from citric acid, for example, and just continuously stirring it with very dilute drops of sodium borohydride. It is not green chemistry, okay? But you add few drops of sodium borohydride. You will directly get with some heat around 60. You will directly get reduction of silver to form silver nanoparticles. The problem is how to keep it and how to investigate and characterize it. But preparation itself is much easier than you imagine. If you get this silver and put it in light, it will be reduced to nanomaterials. If you put it just under light, which is UV light, it will be reduced to nanomaterials. If you added some green materials extracted from plants or something, it will be reduced to nanomaterials. The problem is how to keep it and how to investigate it or characterize it. Adding these silver nanoparticles over these materials is much easier. And we add it in other way, which is the plasma technique. I'll show you something now. And this is the same technique, but using, instead of conventional method, which is the first line, we use plasma to prepare these materials. We prepared magnetite and then prepared added silica in presence of plasma. Then silica formed the first shell, and then we added titania, and titania formed the first shell. Of course, I didn't do it by myself. My student did it. Okay. The difference is, what is the difference, Professor, between doing this reaction here and doing it here? Because if I can do it with conventional method without additional technique, why do what is the benefit of using plasma if we can make it like this, and the plasma will be expensive? Because of this factor. Because of this factor. This factor is, here you can do it in 32 hours. Here you can do it in 7 hours. This is the first factor. Second is, when we measure the catalytic activity of this material and this material, it is completely different. This material has much more catalytic activity in the desired reaction. Let me show you. This is a simple setup of the plasma, where this is magnet and this is beaker, okay? And this is 2 electrodes of plasma, and of course power. This is how it goes. Of course, we used silver as electrode. Here you can see how did we introduce the silica. This is the source of silica, TIUS, and we added dry nitrogen here, and goes to TIUS and carries TIUS with the gas to the medium which has magnetite, and continuous steering in presence of this plasma discharge here for 2 or 3 hours, and it goes to silica will form a shell, And again, we make the same thing with using titanium source to our material in presence of plasma to give us the total FTS material core shell. And this is a picture, and I'll show you a video here. I think this is the preparation of adding silica to magnetite to form silica magnetite core shell. Sorry again. I'll show you this one. This is TEUS. It has it's bubbling here to take nitrogen is bubbling to take here. You can see this is the plasma. This one electrode, and this is other electrode to make plasma discharge, and it makes the it shows forms the core, forms the shell over magnetite core. This is the first one, and the second one is the formation of the other. No, the second one is the second one is the formation of titania shell over. We added titania as a source, so we added the source of titanium isopropoxide. We added titanium source with this is 2 electrodes to make plasma, and continuous steering until maybe 2 hours or 1 hour. It will form the double shell, which is titanium. And we took these materials and make investigation. I will show you how it goes. This is the TEM images of these materials, and you can see the core shell, the core inside the shell, as you can see here, and also we get some data of HR TEM, like here, and these are other HR TEM data, and after decoration with silver. This is silver. This is black point there are silver over FST, which is magnetite. F is silica. T is titania, and decorated with silver. And of course, this is the decoration of silver. You can see it here very clearly. Of course, I'll not go inside these pictures because it will be useless. Only the idea, and you can see how we could prepare it. And I think just this I will only show you. I will not explain in depth, but I will only show you something. This is ESD mapping for the prepared samples. Of course, you can see here different colors. This is another technique to identify the type of material you have. This is different color. The elemental mapping images suggest that iron, silica, titanium, and oxygen atoms were concentrated in the central zone. No, I want to say this. Existence of oxygen in red. This one, this picture means you have oxygen here. The green is silica. This picture means you have silica. Titania is yellow. This picture means you have titania. And the iron is purple, this one. And these points are for silver. I think you can clearly read this data. We didn't invent that this is oxygen, and this we also read or tried to make literature review and discovered not discovered, just understood what other people did, and it is mentioned that these colors means these materials. or these elements. By here, this is UV for this sample, and I'll show you only this one and finish. I am sorry, I make it long today. This is the magnetic susceptibility histogram, and the black one is for Fe3O4. So this is the magnetite, the prepared magnetite. This one, after adding ST, silica, and titania, this one, you can see the 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 difference or the height little bit shorter. It is much decreased. This means that it is chelated or something around it, something isolated from detection. This is only magnetite, and this material is this one, which the magnetic susceptibility decreased in both cases, means the magnetite has shielded with a shell in both cases. And this is the catalytic activity of our prepared samples. Of course, this is a, plasma prepared sample, this one. You can see the concentration of the dye decreased. And this one is no catalyst. And this is only FST, which is the catalyst prepared by conventional method. And this is prepared by plasma method. And this work was published in this journal, which is ACHM, has impact factor 23. It's top 5 journal, alhamdulillah, this year. And now, thank you very much for your attention. And I am sorry I make it late. Thank you very much.
Thank you, Professor Zen. If you have any other query or questions, please, you can ask. Audience, is there any question? Thank you, Professor Zen, for the wonderful lecture from the very beginning. And we'd like to go give thanks to Professor Zen for the first session. Then we'll get a quick break, take a tea, and just come back. Okay? Thank you. Thank you.
Assalamu alaikum. Assalamu alaikum. Now, inshallah, we will talk about our last topic. I think this is our last lecture, inshallah. And I hope everything was going well, all of these lectures. This lecture is talking about zeolites and its applications in catalysis and also in water purification. We will not go through in deep, but because of time, we will just give some ideas about zeolites. Of course, you know that zeolite is a type of a family of porous materials. Porous means, if you remember, sometime I presented a sponge which you use in your kitchen. Everybody here is using it in his kitchen, even male or female, I'm sure. Okay, because I'm using it as well. If you see this sponge, you will find it some pores inside this this sponge. These pores are very important because simply it increases the surface area. If it's like a block, how will you see? How will you get how will be the surface area? Only the surface. But once there are some pores, it means that you increase the surface area because there are more surface will become there, or more surface will be created, and consequently more active sites will be exposed to reactants to contact, and also it will have a new advantage in for zeolites. What is the advantage in zeolite? The most important advantage in catalysis using zeolite is shape selectivity. We will discuss about it later on. Shape selectivity means selectivity based on the shape or on the size of the reactants or products. Let's have a look or have an idea about what's porous catalysis. These are shape of some porous catalysis, some porous materials. It doesn't mean it is porous catalysis or not, but to describe a porous structure, several parameters should be considered, which are pore size and the shape of the pore. The pore size and shape we will need together, and channel dimensionality and direction, composition and the features of channel and walls, etc. Among these parameters, pore size and pore shape are the most important, because pore size means how will be the size of the material it will be absorbed or get in the pores. How large is it? And also the this is the size and the shape. Which shape should be enter this these zeolites? Of course, we know that there are it's classified into three types. The first type is microporous materials, which is the aperture or the opening of the pores is equals or less than 2 nanometers, very small. And there are mesoporous materials. The aperture or the opening of the cavities or the channels or something are from in the range of from 2 to 50 nanometers. And lastly, macroporous materials, which are larger than 50 nanometers. I am not talking about particle size. I am talking about the aperture or the opening of the cave or the channel on the surface of this size of these materials. Again, I mean this one, this one, this, this one, not this one. I mean this opening. This is the aperture this one. If it is 2 nanometers or less, microporous. If it is from 2 to 50 nanometers, it is mesoporous. And if it is larger than 50, it will be macroporous materials. Porous materials may be classified into 3 categories. The first one is organic materials, like polymers. Polymers may be porous or not, and also covalent organic frameworks in general, and porous organic polymers. And the other category is inorganic materials. In our case, zeolites is an example, inorganic materials. And also SAPO, which is silico-aluminophosphate. The third one is inorganic hybrids, which combines and have both the organic part and the inorganic part or section, like adding some metals on the organic materials, which it may be one of these 4 or more functionalized mesoporous materials, or periodic mesoporous organosilicates, or metal organic framework, MOF, or MOF derived porous carbon supported metal oxide nanoparticles. These are the classification of porous materials. Until now, we didn't talk about zeolites. What about zeolites? Actually, zeolites was discovered maybe 200 years or something. It was discovered as some stones which are called boiling stones. Zeolites means boiling stones. These stones or boiling stones or zeolites has a very unique structure or very unique composition. It has only the main structure is a composition of 2 oxides, titanium oxide and aluminium oxide. Titanium oxide and aluminium oxide, as we can see in this structure, titanium oxide and aluminium oxide. And they are arranged as silicon surrounded by 4 oxygen atoms, or aluminium surrounded by 4 oxygen atoms. So the unit, which the repeated unit is Ti or TO4. TO4. T equals silicon or aluminium in both cases, TO4. So TO4 is repeated TO4, whatever it is, silicon or aluminium. Because the change of silicon or aluminium will change the ratio of silica alumina ratio in this structure, which will consequently change the composition and it changes the properties, changes the active sites, changes the pore size, it changes the opening or aperture, it changes if it is the shape of the pores, if it is cavities or channels or something, and also the preparation method will make all of these factors will change, and we can control it. I will tell you how to do it. Of course, these structures will form finally to a negative charge. This negative charge is normalized by the presence of cation. This cation may be any cation like sodium, potassium, calcium, ammonium. Any cation like this will neutralize or normalize the negative charge from this structure. Here I only want to show you how it looks like the natural zeolite. It is like a stone like this. And companies grind it carefully to a specific or desired particle size to form this powder. And this powder is bagged for us to buy it and use it in laboratory or in other industries or other industrial purposes. I want to tell you something, that This is not the only shape of zeolite we can see. There are several shapes of zeolite they discovered, and they were discovering one by one until few tens of zeolites, maybe less than 100 or a little bit more than 100, but they discovered a lot of natural zeolites. And they found that these natural zeolites have very good characters, very good activity in not in catalysis now, because they didn't use it until now in catalysis, but they use it in purification of water. They use it in ion exchange. They use it in filtration. They use it in purposes like this. So they found it also selective in separation of some compounds, because they may absorb some materials or compounds and don't absorb others. As we can see here that uh, I will show it later, but now I'll take you to in a very short trip how they moved from natural zeolite uh, to uh, synthetic zeolites. Natural zeolites and synthetic zeolites. Natural zeolites exhibited ion exchange capacity and ion exchange properties for some cations. How did this ion exchange happen? This ion exchange happened because the presence of those cations we had just mentioned, calcium, sodium, potassium, etc. This makes it easy for them to make ion exchange. Ion exchange means if you have, for example, calcium or magnesium in hard water and put these materials inside the hard water, ion exchange will happen, means these zeolites will absorb or exchange calcium and magnesium from water and leave sodium. Sodium is very easy to get rid later, and it will not make hardening of water. And also it is selective in absorption because they can take some materials and leave others. So it's selective. The other is soon afterwards, scientists began to realize the importance of such materials in industry because it is natural, yes, but it is not sufficient for the expected purposes or the desired purposes from these materials. I remind you again with the synthesis of ammonia. How did they think to synthesize ammonia? Ammonia is there naturally, but very little. So, but they need it more and more. Also, before the World War, the First World War, and the need for increasing the food in this world, what they do, they try to find out fertilizers to increase production of plants for people to eat. And natural fertilizers are not sufficient. So they try to prepare ammonia, to use it in preparation of fertilizers, chemical fertilizers to increase production of plants, and everybody will eat. Although if this didn't happen, of course we will have a problem in to find food at the moment. At this time, they try to find out how to prepare these materials because these materials have great applications in many fields, like separation of materials, like treatment of water, like ion exchange, and also in catalysis later. Uh, so these are the main characters of these materials. The main character of these materials is it they are crystals in crystalline form, and they are found as deposits from volcanic sediments, enclosed alkaline and saline lake systems, and also they are in fresh water lake groundwater, and it is like this, like there. Also, it's found in as a volcanic material. This is where they bring it. Deposits formed from volcanic materials in alkaline soils, and also deposits resulting from what's written there, hydrothermal. Please remember this technique. This is just a word here, but it's a very great technique. We will use it. Hydrothermal or low temperature alteration of marine sediments formation, which are the results of low grade burial metamorphism. Now we go to how did they try to prepare it. From 40, they discovered around 40 types of zeolites, and then discovered the others. So they try to prepare zeolites. At present, natural zeolites are widely used in the fields of drying. This is the purpose of these materials: drying, separation of gases and liquids, softening of hard water, treatment of sewage, melioration of soils, catalysis or supports of catalysts in industry. These what are the purposes of using these materials, and also it has other uses as we will mention later. Inshallah. Because of natural zeolites can't meet the huge demand in industry, so they try to prepare other amounts of other zeolites, synthesized zeolitic materials. Of course, they tried to prepare it in the end of 1960 or 1970, something like this. So they only tried to imitate the conditions where these zeolites have been formed. They tried to imitate the pressure conditions, the temperature conditions, and also the in alkaline mediums. This is how did they characterize or make a kind of these zeolites by this is A. Zeolites as like us. Each one of these zeolites have special fingerprint. These fingerprints, if it is zeolite A, it will be like this. Zeolite Y, it will be also like this, but little bit different. Zeolite X, it will be like this, like cages. This is a cage, okay? It will be like this, but also it has little bit different in aperture, or each one of zeolites has its own fingerprint. And every family of zeolite, because zeolite as a whole is a very big family. And this family is divided to families, different families. These different families are divided to members. So they are a huge number of zeolites have been prepared at the moment. And because we control how to prepare, how much is the silica alumina ratio, how is the conditions of preparation, all of these parameters may produce different types of zeolites which are used in different purposes. Here you can see that each corner of these is either silica, either Si or Al, each corner of these. And each sodalite, this is sodalite. This is colored, this is sodalite, a unit. This some alumina and the silica are connected together to form this unit, and this unit is connected to other units like this to form the cage, and the cage is connected to other cages to form the whole material. And of course, they are very great not thank you, but thank to the people who tried to prepare these materials, and they thank the materials, the preparation methods, or the advancement in the preparation technique, the development of synthetic techniques. Of course, because of these synthetic techniques, they could prepare the zeolites. what are, how could, of course, they imitated these conditions to form zeolites. How could, this is a type of zeolite. This powder is a type of zeolite, and this is its structure. I think it is ZSM5 zeolite. Of course, as I just mentioned, in changing the silica alumina ratio will lead to change the structure, and consequently will lead to change the properties and purpose. Because changing silica alumina ratio, for example, will change the type of cages and channels, and it changes how much acid sites you have, how much basic sites you have on the surface, according to the ratio of silica and alumina. And then later it will change its properties. Like this, a higher silica alumina ratio, the last one, changing the silica alumina ratio significantly impacts their structure, particularly affecting the concentration of acidic sites and the types of phases that can form. A higher silica alumina ratio will decrease in acidity and can influence the formation of different crystalline phases, impacting the zeolites' overall properties and catalytic performance. Changing the silica alumina ratio will change all the story after preparation. These are the methods by which we can prepare the silica, the zeolites. And the first one is the most common one. First one is the hydrothermal method, conventional hydrothermal method. How can we use conventional hydrothermal method in the preparation of zeolite? Do you know how to, what is hydrothermal method? Hydrothermal method where you use the this one, which use autoclave. This autoclave, it's a stainless steel autoclave, like cylinder, stainless steel cylinder, well fitted, well closed fitted, and it is Teflon lined stainless steel, which it has its heart is a Teflon and will close the laces. Let's go back again here. This is the first method, which is a conventional hydrothermal method. Second method, microwave assisted hydrothermal method. Third is fusion and the hydrothermal method. Design and the hydrothermal method. Molten salt method. I think hydrothermal method is very famous, whatever it's accompanied by which technique, but it's very famous in the preparation of zeolites. Why? Because hydrothermal method means you add your materials all. I go here. This is a material. You mix your components like silica source and titanium source, and very important part, which is and template. You use template. Do you know what's template? When they construct this building, they just make a kind of skeleton of wood or any other material like stainless steel or anything, just wood to make it's a kind of skeleton, and then added the concrete. After that, they removed the wood. Concrete is still there with the same shape of the structure of the wood before. That's the template. Template means you add a material. Here, to prepare zeolites, silicon and the aluminum sources are mixed in high pH because, as we mentioned before, that it was formed in alkaline medium. So we add high pH to dissolve silica and the alumina components. Aqueous solution and pH often with addition of structural directing agent, which is the template. You add template. This template is usually it's organic material. This template will build. We will build around it silica alumina structure. It will take the same shape of the template, and then by dissolving this template with a solvent or just little bit heating, it will be evaporated or removed, and your structure of zeolite will be there. I think we talked about this one now, and this is very simple, very simple method or steps. It's just steps. You add silica sol, which is silica source, and in this organic material, which is butylamine, which is a template with alumina source, all will be mixed together, and then they will go to this autoclave. This autoclave will be heated. What is the purpose of this autoclave? This autoclave, it's I am sure you know there is in your kitchen there is a pan which is works under pressure. You just heat. I don't know how to say in English, but temperature, pressure cooker. Okay, this pressure cooker. Of course, you try to imagine this pressure cooker without. Usually, it has a small valve. Without this valve, it will, if you increase the temperature to 100 degree or 150 degree, and the solvent is water inside, what will happen? No. We add it. It's if you imagine this is very strong cylinder, it will not explode. Don't worry. This strong cylinder. We heat it at 150 or 170 or 200, and if you remember, if you go with this temperature under this closed system, water will be evaporated. Of course, it will be evaporated, but at the same time, it will be condensated, and there is circulation between condensed and evaporated water, dynamic equilibrium. At this time, you reach something called supercritical situation. At supercritical fluid, at this time, you reach supercritical fluid. You can't distinguish between vapor and water. Both of them, there is vapor there and water there, but you can't distinguish between two cases or two states. By this, it is cooked together. This means it's cooked together. Under this condition, pressure is high and temperature is high and over boiling point of water and still water there. Then you take it, cool it. You should cool it first. You take it, cool it, and you separate your material, filtration, and then drying. At this time, you get your zeolite. It's here he was working to prepare this M5, but still, this is the general technique for the preparation of any zeolite. Of course, this is not our work. This article was preparing different types of zeolites, like silica, alumina with template. It gave zeolite. The first one is, I think this is the SM5. It is the same shape. The other one has phosphorus. If you add phosphorus, then you will get SAPO, which is silica alumina phosphate. And this is another type. This is mesoporous silica. And this is another story. Another type of zeolite. They are preparing PMO, and this is they are preparing MOF, metal organic frameworks, and of course this is another stories like COF and VOF. There are a lot of preparation methods, lot of types of zeolites you can prepare, and because there are a lot of applications are waiting for these materials. You are preparing these materials to apply for something, because you are not preparing just for fantasy. If you are preparing today for fantasy, just for science, tomorrow somebody will come and use it, and you will use what you already prepared. And these are other types. What are the main properties of zeolites? First of all, it is stable. It's stable, yes, but it has a weak point. I'll leave it until the end of these slides. You can tell me what you think about its weak point. It's stable against temperature. You can heat it for 500, 700, and 1000 degrees C. Also, it has very high melting point until 1000 degrees C. Insolubility, they don't dissolve in water or other inorganic solvents. Okay? But I think this one is a weak point, because if you add these zeolites in very low pH value, it will undergo this, it will dissolve, because leaching of silica or alumina will occur in presence of the strong acid, and also resistance to oxidation. Yes, it doesn't be oxidized. Unique structure. This is a very important part in zeolites. It's unique structure. This unique structure means you can use this structure in your own purpose, because you are preparing these structures for something, as I will show you just now, inshallah. Poor uniformity. Since they are manufactured with precise and consistent pore size, it's all are the same. The pores are the same, uniform, and polarity, because we just mentioned that they have charges which are normalized with cations like sodium or sodium or potassium or ammonia. And the environmental impact, it's very important for environment. It's very important for green chemistry. It has many applications. This is a type of framework. It is like this, and these frameworks, which are channels, are very important. And cavities and the channels. These are the channels of the SM5, and these are the cavities for Y and X and A. All have the same structure, same cavity. It has the property of ion exchange. That's why it is used in water purification and removing hardness of water. And hydration, of course, it has the capacity to absorb H2O from air. That's why it is used in this purpose as well. Shape selective catalysis, and that's why what we look for as people who are working in catalysis. They are looking for this type of property, which is shape selective catalysis. Let me explain what's shape selective catalysis of zeolites. Zeolites have these channel or cages or whatever they have, and they have unique porous structure with fixed pore size and shape. It's very important. Let me show you how much it's important, because this selectivity, these shapes make us to make people try to use it as mass transfer, it has mass transfer effect. Shape selectivity concept, which is the mass transfer effect in zeolite. It has different shapes or different three types of this selectivity. The first one is reactant selectivity. It both have reactant or product or intermediate. How come? Let me show you something here. If you feel, if this is cages or channel of zeolite, and you just entered these three reactants, okay? Of course, only the middle one will be able to enter this channel and go inside and make the reaction, and then leave this the channel or the zeolite, forming the product like this. This means that you have two reactants or three reactants, whatever. Only one of them will go inside the channel or inside the cavity and make the reaction, and the product will leave. This means it is reactant selective. it selects which reactant will go in and mix the reaction. This is an example. If you have N-octane like this, it may go because it is chain, it's straight inside and forms this product, and this product will go out easily. But if it's branched like this, 2,2,4 trimethyl, it is how it will go. Steric hindrance will be there, and the shape will not be suitable to get in the channel, and the reaction will not be completed. This was reactant selectivity. What about product selectivity? If this reactant entered inside and it could form the para or meta products, which one will go and will leave this reaction medium, and which one we will obtain? Here the zeolite will make filtration for me, will make separation, and it will give me this product, and the others will stay there because of steric hindrance. They can't go out. Like in this case, if A enters inside, B and C will be formed. Only B can go out, and C stays there. This means I make filtration, or I could make product selectivity. Which product he can or it can release? This is a case like toluene. It can get inside in both toluene and the alkene. It can get inside and make reaction, and one of the reactants, one of the products can get outside. If other product will be formed, then it will not be released. The third part is restricted transition state selectivity mechanism, and because it is related to the formation of different intermediates. If this is a reactant, this reactant goes inside and the reaction occurs, and then it gives us the product. If this intermediate inside it changed to other shape, this means reaction will not occur, so no reaction will be there. And at this time, I made selectivity from transition state. Like this, like imxylene, which may react inside and gives this product, toluene. But if it goes inside and the changes will happen, so will occur, so no product will get outside. Now I think it's clear here, but tell me if you have some problem or some question about what we said. We can discuss, inshallah, after these slides. We will finish soon. There are 4 properties make zeolites especially interesting for heterogeneous catalysis. It's very important in heterogeneous catalysis. Zeolites are very important in heterogeneous catalysis. I myself used it in more than 15 articles, but I'll show you how it is important. Zeolites have a pore size usually less than 2 nanometers, but there is a pores in the zeolite. This is the first one. Second one is they can make ion exchange, because that's why people uses it for water purification. Others and also to keep some water and ions inside it. Others they have cationic sites. We can exchange. It is the same like ion exchange, and they have weak and strong acid sites. It is there. We can detect it. Of course, we detected it by pyridine absorption, as we mentioned yesterday. They have diversity of changes in pores and channels, and many. That's why they are using in molecular sieving. The most important applications of zeolites are filtration of water. treatment of industrial wastewater. This is the first application. Second application in industry, they have many applications in industry. They light confined molecules within small spaces. All are the most important that we already mentioned. They are used as sorbents and catalysts. Besides, they are used as supports. They are using as catalysts, and also they are used as supports for other catalysts. They are used in gas separation. Additionally, they enable the separation of noble gases, nitrogen, oxygen, and light emission. They are used in lit lamps and in detergents as detergents, and also even used in asphalt, as you can see, and also in vacuum pumps. And finally, I would like to say thank you very much, and I am sorry for this long time. Thank you.
Speaker, Professor Zain home Muhammad Ahmed Ali Al-Bahi to deliver the wonderful lecture. Today the last day and 14th lecture today delivered by Professor Zain. So from the audience, if you need to acknowledge, please say something regarding the course, regarding the lectures and the other things. You visit Jamia Millia Islamia for attending this program organized by the Department of Chemistry, Faculty of Science, Jamia Millia Islamia, and it's a very good scheme. By the for the GIAN program by Ministry of Education, Government of India. So I really acknowledge to the Ministry of Education to give the chance to organize such type of program. So anyone can say, please say something to the for Professor Zain. Yes.
Okay. Yes, sir. Thank you so much for conducting this really informative session, like this program. And I would like to thank Zin sir, because the way he put everything, like his PPTs were simplified, his methods also, and he explained, like you explained everything really well from basics to all the techniques and then application and everything. As myself from not from chemistry background, it was really like easy to understand and easy to get the information. And I think from these 5 days I took a lot with me, that the information and everything, and I kind of develop an interest in green chemistry. I would like to know more and study more about it. So thank you so much, Jane sir, for your guidance and like delivering this really nice series of lectures. And I will also like to thank Resuddin sir for arranging this course in the Department of Chemistry from Jamia Millia Islamia, and also the like GIAN program, the its initiative, like it's for just academic network, so it is also a really good program, and I'm happy to be a part of it. So thank you so much, the coordinates and everything.
Thank you, Shivani. Thank you very much. So anyone?
Assalamu alaikum, sir. First of all, sir, the program was overall fantastic, and the lectures you delivered were all informative. And some may find them the basic. There were discussions that they are basic, but I believe that you cannot grab all the information from a lecture. And in each and every of your lecture, for my personal work, I have got some tips that one can gain with experience only, and we have to learn it at the very early stages of our career. This that will be so beneficial in our learning to that we will not avoid those mistakes that you just provided us directly with the experience you have got in those several years. And regarding GIAN program, it not only just gave us the knowledge regarding our subject or a topic, but we get to know various opportunities and directions we can work on, and we get to meet such eminent personalities that we could never have met without joining this course. And learning with their experiences was really an awesome experience, and we really feel honored to have you here. Along with that, I am really thankful for the coordinators, Raisuddin sir and Professor Saika ma'am. You are the backbone of this program. Otherwise, we would not have been here, and we would never get a chance to meet these people. Thank you so much, sir.
Sir, sir, as I have already told you that there are a lot of people who have knowledge, but not all of them are good at delivering. Actually, I'm not good at expressing, so I won't say much, but you are an orator. For me, you are an orator. And thank you, Rais sir, for making it happen. And thank you so much for inviting me here.
एनीवन? हिंदी में बोल दो, क्या है? अरे हिंदी हमारी प्राइम लैंग्वेज है, हिंदी में बोल दो, जो बोलना है दिल से बोलो, हिंदी हो इंग्लिश हो कुछ भी हो, समझ आना चाहिए.
Good afternoon, sir. Uh, Thank you for inviting me in GIAN program. रईसुद्दीन सर का बहुत दिल से धन्यवाद करते हैं कि आपने हमें यहाँ पे बुलाया. It is my first program, but it is very knowledgeful. और हमारे जीनोम सर, हमें कभी भी ऐसा नहीं लगा कि वो फॉरेन फैकल्टी है. बिल्कुल ऐसा उन्होंने ऐसा दिखाया कि हमारे इंडियन फैकल्टी है. बिल्कुल सिंपल तरीके से एक्सप्लेन करके दिखाया उन्होंने सब चीज़. और हमने बहुत अच्छी वेल डेवलप्ड लैब्स, CIF लैब्स जैसे नैनो पार्टिकल लैब्स देखी हमने जामिया में, पर बहुत अच्छा एक्सपीरियंस हुआ. और जीनोम सर ने हमें बहुत ऐसी ऐसी चीज़ के बारे में बताया जो हमें नहीं पता था. क्यों, हम अभी उस फील्ड में नहीं है कि सब कुछ पता हो. थैंक्स टू जीनोम सर एंड थैंक्स टू रईसुद्दीन सर फॉर इनवाइटिंग अस. थैंक यू.
गुड आफ्टरनून सर. थैंक यू सो मच सर. आपसे मिलके मुझे बहुत मोटिवेटिव फील हो रहा है यहाँ आने के बाद, क्योंकि अभी हम बहुत फर्स्ट स्टेज पे हैं कुछ करने के लिए, अभी बस स्टार्टिंग ही किया है, तो काफ़ी मोटिवेटिव फील हो रहा है यहाँ आने के बाद. और सर से मिलने के बाद तो बहुत ही ज़्यादा अच्छा महसूस हो रहा है. सर यू आर सो काइंड, सो हम्बल. मुझे बहुत ही अच्छा लगा. आई फील सो गुड टू मीट यू. थैंक यू सर.
Okay. Thank you very much for audience. So I acknowledge Professor Zain Hom Al-Bahi sir. So it is with immense respect and heartfelt gratitude that we acknowledge the presence of Professor Zain Hom Muhammad Ahmad Ali Al-Bahi uh, from Al-Azhar University, Cairo, Egypt, for his invaluable contribution to the GIAN program. We are truly honored to have had a foreign faculty as a wonderful faculty, as our special guest uh, of his caliber among us. His profound knowledge, international perspective, and engaging delivery have enriched the learning experience for all the participants. Professor Al-Bahi graciousness, intellectual depth, and dedication to education have not only enlightened uh, enlightened minds but also inspire hearts. We sincerely thank you for traveling all the way from Egypt to be with us and for graciously sharing your time, wisdom, and expertise. Your experience has added immense value to this program, and we are deeply grateful for the opportunity to learn from you. So thank you, thanks again, thank you very much for the participants for attending all the lectures, all the this event wonderfully, and thank you very much for Zen sir. So okay, thank you very much.
सर्टिफिकेट पे नाम लिखा जाएगा। तो प्लीज क्लियरली अपना नाम मेंशन करिएगा। यू हैव टू मेंशन योर नाम वेरी क्लियरली एंड कोई स्पेलिंग मिस्टेक नहीं होनी चाहिए नाम पर। नदीम हो गया स्टार्ट? गुड। पासवर्ड होगा उसमें जामिया 1 2 3 स्मॉल में, जामिया JAMIA 1 2 3। सबका स्टार्ट हो गया ना? टाइमिंग भी स्टार्ट हो गई होगी। जब से आप ओपन करेंगे तभी से टाइमिंग स्टार्ट हो जाएगी आपकी। किसी को कुछ प्रॉब्लम आ रही है तो बता दीजिए प्लीज। There are only 50 questions, so please do not worry. You have to choose only one option.
वीडियो बना रहे हैं तो एग्जाम में सब कुछ बना रहे हैं ताकि चलेंगे all are comfortable for the exam.
रिकॉर्डिंग शक्ल आई
सलीम सर
मैं फोटो खींच के आपको भेज दूँगा।
हाँ बैग आप लोग साइड कर विक्रांत जी जरा देखो फोटो खींच
Dignitaries, esteemed guests, dear participants, colleagues, and my dear students. I, Dr. Zeba, Assistant Professor from Department of Chemistry, feel deeply honored to welcome you all to the valedictory session of this GIAN program entitled In Situ Design and Catalytic Dynamics of Nanomaterials for Water and Air Quality Monitoring and Mitigation, which was held between 28th April to 2nd of May 2025. So I request our esteemed dignitaries, Professor Saiduddin Sir, Dean Faculty of Sciences, uh, Professor Zeenhom Muhammad Ahmed Al-Bahi Sir, our foreign expert, Professor Atiqur Rahman Sir, our local coordinator GIAN program, and both our course coordinators, Dr. Raisuddin Sir and Professor Saikha Ma'am, to kindly escort our guests to the dais. Thank you, everyone, for joining us today for this concluding session. So, as we reflect on this enriching journey, let us be inspired by the words of Madame Marie Curie. And she said that one never notices what has been done, only one can see what remains to be done. So, with this quote, I leave up to the audience that there's a lot to do whenever we disperse after this event. And we have been graced by our foreign faculty, Professor Zeen Sir, who has very actively, interacted with all our young participants. So I request Professor Atiqur Rahman Sir to kindly felicitate Professor Zenhom Sir by offering a memento as a token of love and respect. थैंक यू जी जो हमारा फर्स्ट डे वाला प्रेजेंटेशन ज्ञान वाला था उसको प्लीज बैकग्राउंड में चला दो आमिर इज हेयर अराउंड इज आमिर हेयर विक्रांत भाई वो फर्स्ट डे वाली प्रेजेंटेशन चला देंगे आप इट वाज देयर ऑन दैट हाँ सिस्टम इटसेल्फ हाँ ठीक है मे बी ऑन द स्लाइड शेयर शो मोड अगर चल जाए अच्छा कोई बात नहीं इट्स ओके So moving ahead, I request Professor Nasimul Huda sir to kindly felicitate our Dean sir, Professor Saiduddin sir, for his gracious presence and always blessing us. I request Professor Saiduddin sir to please felicitate Atiqur Rahman sir, our local coordinator for GIAN program. Thank you, sir. So now we move on to the most awaited moment of this entire session. And I'm very happy to announce that we had almost 90% participation for the examination which was conducted in the last session. In the entire 5-day program, we had around 13 technical lectures, and each day we had tutorials. and we had 63 registered participants for this program from all over the country. So I'll be calling upon the names of the participants. I would request them to come soon after their names are being announced. I request our Dean Sir to kindly confer these certificates to our participants. Afreen Jahan, Miss Afreen Jahan. हाँ sir, आगे आके. Tuba, are you here around? Can you please come here? I'll call upon names and you please pass it on to sir. आफरीन जहां, आप इधर आ जाओ साइड में. तुबा इधर आ जाओ. Shakil Alvi, Mohammad Fadeen. Fadeen is there. जल्दी जल्दी प्लीज जी. अस्मा, आमिर. अच्छा. मोहम्मद सुफियान आलम. काजल अग्रवाल. इरम. इरम is also. बेना. अलीजा खान. अलीजा is there. आसिया अकील. याशिका. प्रेरणा राणा. अदिति पालीवाल. Aditi is not there, I guess. You are there, Aditi? Oh, okay. Achha. Please come fast. Sanjana. Aditi Paliwal. Sir, Aditi Saxena, I guess her certificate is down. कोई बात नहीं. Yeah. Nitika Meena. Lokesh Kumar. I'll change it, sir. Sure. Hemendra Pratap Singh. Himanshi Goyal. Deepa Dhandli. Mohammad Nadeem. Nadeem is there. We thank Professor Saiduddin, sir. Thank you, sir. Now I would request Professor Atikur Rahman, sir, to kindly confer these certificates to our participants. Danishta Parveen. Mariam Fatma. Mohammad Zaid. Mohammad Zaid. Sayyid Zainab Hassan. Rizwan Arif. Disha Mishra. Buddhdev Gautam. Disha Mishra. Sir, वो Gautam sir. Nimi Pawar.
every second is being recorded. So this was the far most important facility which was desperately needed, and we are greatly thankful to Director CIT as well. As my dear colleague Zeba, she always take a quote from Marie Curie. She is the one, in fact, she is a role model to all the female scientists. So, and I really admire her. And if you go to my Facebook page, you'll find that I have a particular quote of her on my Facebook wall, which is state, "Fall in love with more frequently with the ideas, not with the people. These are the one which never betrays you." So again, I thank you all with the concluding remark, uh, with a quote of that was said by Michelle Obama. We learned about honesty and integrity, that the truth matters, that you don't take shortcut or play by your own set of rules, and success doesn't count unless until you earn it fair and square. So with this quote, I thank you all on behalf of Department of Chemistry and Jamia Millia Islamia. I wish you, and we all wish you a great success and good luck. Thank you so much for being here. Thank you. Uh, I request everybody to please gather outside to have a concluding valedictory photograph, a group photograph, and then we'll be having a high tea and guest house. And with this, I conclude and I announce that the program is over. Thank you.